When a black body is heated to a high temperature, it emits a characteristic spectrum of light that depends on its temperature T. Here is how the spectrum looks like. If you plot the emitted spectral energy density, rho nu, in units of joule per cubic meter, against the frequency of the emitted light, nu, in hertz, we get curves starting at 0, going through a maximum, and approaching 0 with increasing frequency again. With increasing temperature, the overall energy density becomes larger, and the spectral maximum shifts. Examples of black bodies at high temperatures are the stars, the sun, heated pieces of metal, and incandescent light bulbs. This black body radiation spectrum cannot be explained by classical theory. In fact, it fails spectacularly, as it predicts that the body would emit an infinite amount of energy. Quantum theory gives the correct picture. Assuming that the black body can only emit energy in multiples of h nu, that is, as photons, the energy spectral density can be derived. It depends on the frequency and the temperature and is given by rho nu of nu and t times d nu equals 8 pi times the Planck constant over the speed of light cubed times the frequency cubed divided by e to the power of h nu over kBt minus 1 times t nu. This is called the Planck law. After Max Planck, who discovered this relationship in 1901, this discovery started the entire age of quantum theory. You can obtain the Planck constant from this by fitting the equation to an experimental spectral curve and extracting the fitted value for h. The maximum of the black body emission spectrum increases with increasing temperature. In terms of wavelength, it is given by lambda max equals hc divided by 4.965 times the Boltzmann constant times 1 over t. That is, the maximum wavelength decreases with increasing temperature. This equation is known as the Ween Displacement Law. It can be used to estimate temperatures of stars from their emission maximum. For example, a black body at 3000 Kelvin, a fairly low temperature for a star, has a spectral maximum of about 965 nanometers.